In the face of mounting environmental challenges and an increasingly unpredictable climate, the resilience of infrastructure has emerged as a critical global priority. Engineering technology, with its rapid advancements and innovative solutions, plays a transformative role in enhancing the durability, adaptability, and recovery capabilities of essential infrastructure systems. Today's cities and communities are not only seeking to withstand natural disasters, but also striving to recover swiftly and adapt proactively to future risks. The integration of cutting-edge engineering technologies into infrastructure design, construction, and maintenance is redefining the possibilities for resilient urban environments. One of the most significant contributions of engineering technology to infrastructure resilience lies in the development of advanced materials. Traditional building materials often fall short in the face of extreme weather events or prolonged environmental stressors. In response, engineers have pioneered high-performance composites, self-healing concrete, and corrosion-resistant alloys that dramatically improve structural longevity. For example, self-healing concrete contains microcapsules of healing agents that automatically seal cracks when they occur, preventing water ingress and steel reinforcement corrosion. Such innovations reduce maintenance costs and prolong the functional life of bridges, roads, and buildings, ensuring that communities remain connected and safe even after adverse events. Beyond materials, the integration of digital technologies such as building information modeling, BIM, geographic information systems, GIS, and Internet of Things, IoT, sensors has revolutionized the way infrastructure is planned, monitored, and managed. BIM enables engineers and planners to create detailed, dynamic models of infrastructure assets, allowing for scenario analysis and risk assessment long before construction begins. Through GIS, authorities can map hazard-prone areas, optimize evacuation routes, and identify critical vulnerabilities across vast networks. Meanwhile, IoT sensors embedded in structures provide real-time data on stresses, vibrations, temperature, and humidity, allowing for predictive maintenance and early warning of potential failures. This convergence of digital tools supports a proactive approach to resilience, shifting the focus from reactive repairs to anticipatory action. The rise of smart infrastructure is closely linked to the proliferation of artificial intelligence, AI, and machine learning algorithms. These technologies process vast amounts of data collected from sensors, satellites, and public sources to detect patterns and predict emerging threats. For instance, AI-driven flood forecasting systems analyze historical rainfall, river flow, and terrain data to provide accurate, timely warnings to residents and emergency services. Similarly, machine learning models can assess the structural health of bridges and tunnels by identifying subtle changes in the sensor data, prompting timely interventions before minor issues escalate into catastrophic failures. By harnessing the power of data and intelligent analytics, engineering technology enables infrastructure managers to make informed decisions that enhance resilience and reduce downtime. Another area where engineering technology is making a profound impact is in modular and prefabricated construction methods. These approaches allow for the rapid assembly of infrastructure components in controlled environments, minimizing exposure to weather-related delays and quality inconsistencies. In disaster-prone regions, modular construction enables the swift deployment of temporary shelters, hospitals, and utility systems, ensuring that essential services are restored quickly after an event. Moreover, prefabricated elements can be designed with resilience in mind, incorporating shock-absorbing joints, flexible connections, and elevated platforms to withstand earthquakes, floods, and storms. Such adaptability is crucial in reducing recovery times and safeguarding vulnerable populations. Resilience is not solely about withstanding shocks. It is also about adapting to long-term changes. Engineering technology facilitates this through the concept of adaptive infrastructure, systems that can evolve in response to shifting conditions. For example, coastal cities are employing adjustable seawalls and flood barriers equipped with sensors and automation, which raise or lower in anticipation of tides and storm surges. Urban drainage systems are being reimagined with permeable pavements and green roofs that absorb rainfall, reducing the risk of flash flooding. These adaptive solutions, made possible by advances in materials, science, robotics, and environmental engineering, ensure that infrastructure remains effective under both current and future climate scenarios. Collaboration and information sharing have also been enhanced by engineering technology, fostering a more integrated approach to resilience. Cloud-based platforms enable stakeholders, from engineers and architects to emergency responders and policymakers, to work together seamlessly, sharing real-time updates and coordinating responses during crises. Digital twin technology, which creates virtual replicas of physical assets, allows for continuous monitoring and simulation of different disaster scenarios, supporting strategic planning and resource allocation. By breaking down silos and promoting interdisciplinary cooperation, engineering technology ensures that resilience is embedded at every stage of the infrastructure lifecycle. Furthermore, engineering technology is empowering communities through participatory design and citizen engagement tools. Mobile apps and interactive platforms allow residents to report hazards, monitor infrastructure conditions, and contribute local knowledge to resilience planning. This bottom-up approach not only improves the accuracy of risk assessments, but also fosters a sense of ownership and preparedness among community members. When citizens are actively involved in shaping their environment, infrastructure systems become more responsive to local needs and better equipped to handle disruptions. Sustainable energy systems represent yet another frontier for enhancing infrastructure resilience. Microgrids, solar panels, and energy storage technologies are enabling communities to maintain power during grid outages caused by storms or cyber attacks. Decentralized energy solutions reduce dependence on single points of failure and can be rapidly deployed in remote or disaster-affected areas. Engineering advances in renewable energy integration, battery management, and smart grid control are ensuring that critical facilities, such as hospitals, water treatment plants, and communication networks, remain operational when they are needed most. In conclusion, engineering technology is fundamentally reshaping the landscape of infrastructure resilience. Through innovative materials, digital intelligence, adaptive design, collaborative platforms, and sustainable systems, engineers are equipping our built environment to face the uncertainties of the future. As challenges grow more complex and interconnected, the synergy between technological innovation and resilient thinking will be essential for safeguarding societies against both immediate shocks and long-term transformations. By embracing these advancements, we are not only building stronger infrastructure, but also nurturing more resilient, adaptable, and thriving communities for generations to come.